Okay, so I'm going to be talking about periodic variations and element properties. So this isn't like one category per se, it's like a broader stem of a bunch of ways that we arrange the periodic table to show certain things. So since the periodic table was kind of edited and changed a little bit over time, there's not like one clear inventor per se of the way we organized it. There were a couple people who were pretty key originally, but we've changed it a bit to account for new discoveries because we're still kind of figuring it out. So the three main trends or categories of periodic variation that we're going to talk about are atomic size, ionization energy, and electron affinity. So atomic size refers to the radius of an atom. And so the way the periodic table is arranged, atoms are larger in radius, proceeding lower and to the left side of the periodic table. So from left to right, they actually decrease in size. But not necessarily in weight or density, it's just in radius. So we have a graph here that shows by atomic number. There's a way to do it. We have the larger atoms at the top, and then we have transitional elements that are usually to the right side of the table. So if you look at the periodic table, right, if you have by atomic number, it goes left to right, and then back to the left where the larger ones are. So the second topic is ionization energy. So ionization energy is the energy required to remove an electron from a gaseous atom or ion. The first or initial ionization energy, this is the upside down exclamation mark, of an atom or molecule is the energy required to remove 1 mole of electrons from 1 mole of isolated gaseous ions. And it's measured in kilojoules per mole. So if we look at the periodic table, it's the exact opposite of atomic radius. So we have ionization energy gets larger as we go up and to the right on the periodic table. So then the last topic is electron affinity. So it's the amount of energy released or spent when an electron is added to a neutral atom or molecule in a gaseous state to form a negative ion. So if we had neutral element X and we wanted to add an electron, so we get X gaining an electron, it's the amount of energy released in that reaction. So here's a way to explain it. If we look at the periodic table, we have the largest amount of energy used in that reaction is in the noble gases. So because they have 8 valence electrons, adding an electron takes a lot of energy because it has to go to a higher energy shell because all of the shells are filled in row 8A. So the larger the electron affinity coefficient to the right of the periodic table, the higher energy electron shell the new electron must take a place in, right? So that's why in the noble gases it would have to go into a P shell, I think.
It's completely filled, so it'll go to the next S shell.
The next S shell, right. So thus a reaction releasing more energy takes place. A larger amount of energy is released in elements from left to right across the periodic table with a couple exceptions right here, and I'm not really sure exactly why. But okay, so here's the problem. Put the following elements in order from least to greatest atomic radius, H, E, C, S, B, and O. Anyone got the answer?
Yes.
So since we're proceeding downward, right, from helium and cesium is the largest, at the bottom left it would be H, E, O, B, and cesium.
Anybody have any questions for Jacob?
So
Which was thinking of the question.
yeah. In conclusion, periodic variations of element properties isn't like one category. Again, it's several categories. It's simply the way that we set up the periodic table to show more than one factor about each element.
I have a couple of questions. It's not just for you, for anybody can answer. So who were the two people who mainly created the periodic table or who are well known for the
I
periodic
know its
table?
name, his
Yes.
name, but it's really,
Anybody? Mendeleev, right?
Yeah.
He's a Russian physicist or
Yeah.
who created. And I had one more question. What is the trend of the atomic radius? Can you tell me?
atomic
How is it?
radius. So atomic radius, the smallest we have helium, and it goes, generally, the radius grows as we go down and to the left on the periodic
Why
table.
is that?
Because not quite sure. So I know that the noble gases are smaller in radius because they are more stable and they're not more dense, but they have a stronger pull. The electrons do to each other, or not the electrons, the nucleus. It's more compact.
Why is it?
I'm not sure.
So think about the number of electrons and the number of protons that present in that. So they have more number of protons and more number of electrons, right? And they are all in the same shell.
Yeah.
Right? It gets, as you go from left to right across the periodic table, the same shell gets filled up. Right? So when all the electrons are within the same shell, the attraction to the protons, with the electrons, they have a greater force of attraction, right? Because all the electrons are in the same shell, they are getting filled in the same shell. Whereas when they go to the next period, the next shell comes into account, right? So it increases in one shell. So the electrons start to get filled in the next shell, right? So that shell does not have that much attraction to the proton as the previous one. So the atomic radius, that's why the trend, it increases when it goes to the next period. Thank you, Jacob. That's a good discussion.